Hi, my name is Haris Aziz, and today I'll be presenting my WINE paper, which is titled Simultaneously Achieving Ex-ante and Ex-post Fairness. So let's begin. We're considering a setting in which agents have additive positive utilities over indivisible items. It's a very standard setting in multi-agent resource allocation. And the outputs that we are focusing on are probability distributions over integral deterministic allocations. So people have been considering fair allocation of indivisible items for decades. There's also been plenty of work on fair probabilistic allocation of indivisible items. The challenge that we consider in this particular paper is that of simultaneously achieving good fairness properties, both from an ex-ante point of view and also an ex-post perspective. We will also focus on combining it with efficiency concepts, in particular those based on Pareto optimality. So before we proceed, let's look at a simple example. This is an example with two agents and three items in which agents have the following utilities over the items illustrated in the table. For example, agent 1 gets utility 5 for item A, 3 for item B, and 2 for item C. So one possible way or one possible outcome for this problem could be that we toss a coin, and if it's heads, we give all three items to agent 1, and if it's tails, we give all three items to agent 2. From an ex-ante perspective, this outcome is quite fair because both agents have equal opportunity to get all the items. On the other hand, if we consider ex-post concerns, then obviously neither of the two integral allocations in this probability distribution are fair because the agent who gets no items in both of these allocations, that particular agent would be quite unhappy. So we want to capture this level of happiness or fairness, and this is what we do with the help of a very famous concept called envy freeness, which requires that no agent should envy another agent. In a combination of fairness, we will also consider Pareto optimality, which requires that there exists no other outcome which all agents weakly prefer and at least one agent strictly prefers. So both of these concepts, envy freeness and Pareto optimality, can have an ex-ante as well as an ex-post version, which we illustrate in this figure. Note here that instead of considering ex-post envy freeness, I have listed a weakening of ex-post envy freeness by listing ex-post EF1, which stands for envy freeness up to one item. And the reason for considering EF1 instead of EF is simply because envy freeness is not guaranteed to exist when you have indivisible items and deterministic allocation. All right, so among these concepts, let's check which concepts we can achieve. And we start off with some discussion on ex-post envy freeness up to one item, which is nothing more than finding one particular allocation which satisfies EF1. So as far as EF1 is concerned, there are many algorithms which return a deterministic integral allocation which satisfies EF1. Some prominent ones include Lipton et al.'s envy-free cycles algorithm and also the maximum Nash welfare rule of Karianis et al. What about ex-ante envy freeness? Again, there is the competitive equilibrium with equal incomes rule. Similarly, there is a probabilistic serial rule of Bogomolai and Moulin, which was later extended to take care of weak preferences and Pareto optimality. So it's a nice extension of the original algorithm of Bogomolai and Moulin. So since I'll be focusing a bit more on ideas behind the probabilistic serial rule, let me just explain how it works. So this is an example which has three agents and three items, and the way this algorithm works is that agents start eating the most preferred items which have not yet been completely consumed. We simulate this eating process, so it can also be viewed as the eating algorithm. And finally, the probability that an agent has for getting a particular item is exactly the share or the fraction of the item that she has eaten. So in this case, agent 1 ate 3/4 of O1. And for that reason, we specify the probability of agent 1 getting O1 as 3/4. What else? Well, this issue of simultaneously satisfying ex post and ex ante and freeness has been considered recently by Freeman et al. In their ACM EC paper. And what they showed in their paper was, among many results, was one that they came up with an quite an involved algorithm which returns an ex post EF1 as well as an ex ante and free allocation. And they also showed that if we focus on the combination of exposed envy free up to one item, X anti envy freeness, and a property called X anti FPO, which is stronger than X anti Pareto optimality, then these three properties cannot be simultaneously satisfied. So what we do in this paper is that we dig deeper. We ask some fundamental research questions. In particular, we ask whether X post EF1, X anti EF, and X anti SD and SD efficiency, which is a very weak notion of Pareto optimality, whether they can be satisfied. Is there a way to return the probabilistic serial outcome as a convex combination of envy free up to one item allocations? And finally, we just want to get a clear understanding of which sets of properties are compatible or incompatible. So this is what we set out to do. And the first result that we have in this line of work is an algorithm which satisfies all these four properties highlighted in green. We refer to it as the EPS-lottery algorithm, where EPS stands for an extended version of this probabilistic serial eating algorithm that I explained in one of the previous slides. So why I like this algorithm is, apart from it satisfying nice properties, it combines ideas from network flows, probabilistic serial, and some of the most famous algorithms in matching theory. So instead of giving you a pseudocode or an abstract explanation of this algorithm, I'll simply give you an illustrative example. So this is an example which has two agents and four items, and the preferences of the agents are as follows. The reason I've not mentioned the utilities of the agents is because this particular algorithm, it only takes into account the relative ranking of items in the agent's preference relation. So the first thing that we do is that we first find the ex ante outcome as a result of the EPS algorithm of Kata and Sethuraman, and this is done via parametric network flows. The moment we get this allocation, what we know is that this particular allocation satisfies ex ante envy freeness. It also satisfies ex ante Pareto optimality in an ordinal sense. But what we don't know is how to return this as a convex combination of EF1 deterministic allocations. And this is part of the challenge. So the next step that we have here is that what we do is we create representative agents of each of the agents. So, for example, agent 1 will now have two representative agents, and agent 2 will have two representative agents as well. And what these representative agents do is that they take their main agent's allocation and they come in successive turns. And each agent, just like in the probabilistic serial rule, it eats one unit of the most preferred part of their main agent's allocation. By doing so, what we get is that now we have a new allocation in which each representative allocation gets unit one of items. And this turns the resultant allocation Q prime into a form which is a biostochastic matrix. And this makes it quite convenient for us to apply the famous Birkhoff's algorithm directly on this particular matrix. And this gives rise to these permutation matrices, and what we get is that the previous matrix is now returned as a convex combination or a probability distribution over these two allocations represented by permutation matrices. The moment we have this information in hand, what we can do is whatever amount was eaten by the representative agents of one particular agent, that amount of items can again be combined to get the allocation that we have for each of the agents. So both of these matrices, which are permutation matrices, are changed into slightly different matrices in which we ignore the representative agents completely, and we go back to the case of the original agents. And now we have a form in which we actually have a probability distribution over two deterministic integral allocations for the main problem. And what we can prove here is that both of these allocations that we compute, and in general, any of the allocations involved in this probability distribution, they are satisfying this property called EF1, or envy freeness up to one item. So what we have seen is that we can easily achieve ex-ante envy freeness, ex post EF1, and also some ordinal notions of Pareto optimality, which ignore the utilities, but they take into account the preference relations over uh, indivisible items. What more can we do? Well, it turns out that the positive result that we had in the previous slide regarding our EPS lottery algorithm, in some sense, it satisfies a maximal set of properties because we have two new impossibility results which say that certain sets of properties are incompatible or they cannot be simultaneously achieved. In particular, ex-ante SD envy freeness, which is a very strong envy freeness property, ex post EF1 and ex post PO are incompatible. Similarly, ex-ante FPO, which is a very strong notion of ex-ante Pareto optimality, and ex-ante SD envy freeness, which is a very strong notion of envy freeness, are both incompatible as well. So both of these incompatibility results or impossibility results are represented in this figure, where we have these two impossibility statements. Apart from our impossibility and possibility results, we also have some computational theorems. For example, we show that if you're given a random allocation uh, in which we only have the ex-ante information, then checking whether this particular allocation can be implemented by a lottery over EF1 and Pareto optimal allocations is an NP-hard problem. And you get a similar kind of theorem for if you replace EF1 with this stronger property called SDEF1. So almost all of our results are captured in this particular figure, where the results in green show which properties can be simultaneously satisfied, whereas the results in this light pink color show or illustrate our impossibility results. In terms of open questions, we reiterate one question that was originally posed by Freeman et al. In the EC paper, and that is whether there exists a mechanism or whether there exists an allocation which is always ex post EF1, ex ante envy free, and ex post Pareto optimal. And it's still unclear whether there always exists an allocation which satisfies all these three properties at the same time. This is probably the most interesting open question from our study. And in case this study on probabilistic allocations is of interest to you, then this is a plug for a book chapter of mine called Probabilistic Approach to Voting, Allocation, Matching, and Collision Formation. And this was published last year in a book on the future of economic design. So if you're interested in these topics, I suggest you to take a look at this book chapter as well. With this, I thank you for your attention. And if you have any questions, you're most welcome to contact me by email or some other way. Thanks a lot.